Hello students, welcome to the lecture on techniques of integration, and after the lecture we will be able to learn the following objectives. Explain antiderivatives, understand the integration by substitution, define integration by parts. Let's start with a brief introduction to the job description and performance appraisal. Evaluating integrals by applying this basic definition tends to take a long time if a high level of accuracy is desired. If one is going to evaluate integrals at all frequently, it is thus important to find techniques of integration for doing this efficiently. A powerful class of techniques is based on the observation made at where we saw that the fundamental theorem of calculus gives us a second way to find an integral using antiderivatives. The drawback is that antiderivatives often cannot be expressed in closed form, that is, as a formula in terms of named functions.
Welcome back. Today we'll be talking about the antiderivative and indefinite integration. Let's say I give you the derivative of a function and ask you to determine the original function. If f prime of x is equal to 2x, then what would f of x be? Meaning, what would the original function have been if the derivative is equal to 2x? So if you know your derivative formulas well, you might tell me that f of x is equal to x squared. And how could we check that? We could find the derivative of this and verify using the power rule that the derivative would be 2x. But are there any other functions that would also give the derivative of 2x? And in fact, there are others. For example, f of x equal to x squared plus 1, or f of x equal to x squared plus 2, because we know the derivative of a constant is 0. So in fact, there would be an infinite number of functions who have the derivative equal to 2x. Along the same lines, if I told you the derivative of f of x was equal to 3x squared, you could tell me that the function could have been x cubed, or x cubed plus 1, or in fact x cubed plus any constant. So in fact, what we do in these cases is we put plus c to represent any constant. Okay, so let's formalize the definition of the antiderivative. The reverse of differentiating is anti-differentiating, and the result is called the antiderivative. So we were just finding antiderivatives. A function big f of x is the antiderivative of f on an interval I if the derivative of big F is equal to the original function f of x. You can represent the entire family of antiderivatives of a function by adding a constant to a known antiderivative. This is the plus c that we were just talking about. So if big f of x is the antiderivative of f of x, then the family of antiderivatives would be given as big F of x plus c. The process of anti-differentiation is often called integration or indefinite integration. To indicate that the antiderivative of f of x equals 3x squared is equal to big F of x equals x cubed plus c, we write it using this notation. We say the antiderivative or indefinite integral of 3x squared with respect to x is equal to x cubed plus c. This symbol here is called the integral sign. This function f of x is called the integrand, and this dx on the end represents the variable of integration. Of course, big F of x is our antiderivative, and c is the constant of integration. Now there are a bunch of formulas to help us find antiderivatives or to perform indefinite integration, and they're all listed here. And what you'll hopefully notice is that these are pretty much the opposite of the differentiation process. You may want to pause the video here to review all of these. We want to determine the indefinite integral for each of these. So the first thing, if we wish, we can break this up into 3 different integrals. Now often we'll skip this first step and just integrate each term individually, but for this first example I will show this. So now what we're going to do is apply the power rule of integration. So we're going to add 1 to the exponent, 3 plus 1 would give us 4, and then divide by the new exponent, plus 2 times, this is x to the first, so we add 1 to get x to the second, and then we divide by 2, minus the antiderivative of any constant is going to be the constant times x, so 1x, or just x, and we can't forget our plus c, our constant of integration. Now we need to kind of clean this up a little bit, and we're done. Here the 2 and the 2 simplify, and that's pretty much it. So our final antiderivative would be, now we can leave it in this form where we could write it as 1/4 x to the fourth plus x squared minus x plus c. Now, just like when we were finding derivatives, if we want to find the indefinite integral of this, we are going to have to rewrite it using rational exponents. This would be x to the power of 1/2 minus 5x to the 2/3 power. Now again, I could break this up into two different integrals, but I'm going to leave it as it is and just integrate them individually. So I'm going to add 1 to 1/2, that would be 3/2, and then divide by the new exponent, minus 5 times the antiderivative of x to the 2/3 power. Well, if I add 1 to 2/3, I'd have 5/3, and then divide by 5/3, plus c. Remember, a fraction bar is a division symbol, so dividing by 3/2 is the same as multiplying by 2/3. So in the second term, instead of dividing by 5/3, we'll multiply by 3/5 and simplify where we can. This 5 and this 5 will simplify. So our antiderivative would be 2/3 x to the power of 3/2 minus 3x to the 5/3 power plus c.
We will now study integration by substitution. We converted a couple of general rules for differentiation: the rule for the derivative of a constant times a function and the rule for the derivative of the sum of two functions into equivalent rules in integral form. We will develop the integral form of the chain rule and see some of the ways this can be used to find antiderivatives. Suppose we have the functions f and g with corresponding derivatives f and g. Then the chain rule are shown as on the screen. If we now take the indefinite integral of these equations, which is on the screen, where c can be any constant, the integral form reversing these equalities to get a statement about integrals, what we obtain is on the screen.
Of x times the square root of x squared minus 9. Now you'd probably solve this using the method of substitution. You'd probably think substitute for the x squared minus 9 part. But how would you solve the definite integral from 3 to 5? Same integrand. It turns out that you can use the method of substitution for a definite integral as well. And I want to show you how to do that. So let's copy this down. The integral from 3 to 5, x times the square root of x squared minus 9. So we'll substitute for the x squared minus 9. W equals x squared minus 9. And dw will equal 2x dx. Now I don't have a 2x dx, but I do have an x dx. So I can just divide both sides by 2 and get 1/2 dw equals x dx. That'll take care of everything inside the integral, but it does not take care of the limits. These limits are x values. When I change this integral over to w, I really should change the limits to w values as well. And you can do that using this substitution, right? X equals 3, for example, this bottom limit. If you plug 3 in here, you get 9 minus 9 is 0. W equals 0. So the 3 is going to turn into a 0. And x equals 5. If you plug that in here, you get 25 minus 9. W is going to be 16. So my new integral is going to be the integral from 0 to 16. The square root of x squared minus 9, that'll be root w. The x dx, 1/2 dw. So I'll pull the 1/2 outside. Integral from 0 to 16, w to the 1/2 dw. This is 1/2, and now I need an antiderivative for w to the 1/2. I raise the exponent by 1 to w to the 3/2 and divide by 3/2, which is the same as multiplying by 2/3. So this is 2/3 w to the 3/2. And I want to evaluate this from 0 to 16. Now 1/2 times 2/3 is 1/3. So it's 1/3 16 to the 3/2 minus 1/3 0 to the 3/2. Now, of course, this is going to be 0. But what's 16 to the 3/2? Whenever I have a fractional exponent, it depends on what the input is as to whether I want to cube first or take the square root first. But but this number is a perfect square, so I'm going to take the square root first. The square root is 4, then raised to the third power is 64. So this is 64 thirds. And that's my answer. So the neat new trick here is switching over the limits of integration using your substitution. Remember, this formula tells you how. These are x values. Plug them in here, and you can get the corresponding w values.
Trigonometric substitutions. Trigonometric substitutions or trigonometric functions provide a rich set of interconnected functions that show up in many problems. It is useful to remember three very important trigonometric identities that help to simplify many integrals. These are essential trigonometric identities which are shown on the screen. In the special case that a equals to b equals to x, the last two identities above lead to as shown. Double angle trigonometric identities as shown on the screen. From these we can generate a variety of other identities as special cases. We list the most useful below. The first two are obtained by combining the double angle formula of cosines with the identity sine 2x plus cos 2x equals to 1. Let's learn about integration by parts. The method described here is important as an additional tool for integration. It also has independent theoretical stature in many applications in mathematics and physics. The essential idea is that in some cases we can exchange the task of integrating a function with the job of differentiating it. The idea rests on the product rule for derivatives. Suppose that ux and vx are two differentiable functions, then we know that the derivative of their product is shown on the screen. Or in the differential notations as shown. Integrating both sides we obtain as shown here on the screen. We write this result in the most suggestive form as shown here on screen. The idea here is that if we have difficulty evaluating an integral such as interrogative u dv, we may be able to exchange it for a simpler integral in the form of interrogative v du.
So in this problem we're going to do another integration by parts, but let's also just make it a definite integral just to make things a little bit different than the last problem. So again, recall the integration by parts formula says the integral of u dv equals uv minus the integral of v du. Okay, so in this problem I see an ln of x, and you have to be careful, kind of visually looking at it you see an x squared, but really this is 1 over x squared. So we'll have to pick u to either be ln of x or we'll have to pick u to be 1 over x squared. In my problem, again, as a rule of thumb, and you know, it's not an always correct rule, but we'll pick u to be the thing that gets more simple when you take the derivative of it. So if you think about 1 over x squared, that's equivalent to x to the negative second. Well, the derivative of x to the negative second will be negative 2 x to the negative third. Alright, you know, it definitely changes. I don't know that that's better. The ln of x, when you take the derivative of that, though, will become 1 over x, and I kind of like that. You know, there's something about ln's I don't like, and if I make it into 1 over x, you know, something to think about is you also have these other powers of x floating around. Maybe something will cancel out. So I'm going to pick u to be ln of x. I'll pick du to be, well, not pick. If you use ln of x, du becomes 1 over x dx. That means I'm picking dv to be the 1 over x squared or x to the negative second dx term. And if you find the antiderivative of x to the negative second, we'll get x to the negative first divided by 1, or negative 1 over x. Okay, so let's plug all this stuff in here. It says, if I use my integration by parts formula, it says we'll get u, which is ln of x. It says we'll multiply that by v. Okay, so here's v. I'll pull the negative out front and just make it 1 over x. And now the idea is, since this is a definite integral, I'll put my upper and lower limit in there, and we could evaluate this part just like normal. Plugging in the upper limit, subtracting away the lower limit, minus, now I still have an integral left over. It's going to be from 1 to 2, same limits of integration, of v du. So v is negative 1 over x, du is positive 1 over x. If I pull this negative out front, I'm going to get a positive 1 over x squared. But again, 1 over x squared is the same thing as x to the negative second dx. Okay, so we're getting pretty close here. I'm still not going to evaluate this part just yet. I usually save it till the end. And I've seen some confusion in the past. People feel like we're doing some sort of substituting and the limits of integration should change. But notice my variables never change. I always keep x's in the problem, which means I should always keep my original limits of integration in the problem as well. Okay, so the negative ln of x, 1 over x, from 1 to 2 is going to drop right down. Again, if I integrate x to the negative second, well, I already did that up here. It says I get negative 1 over x, so that's going to make the positive into a negative 1 over x from 1 to 2. And now all I have to do is plug in my upper and lower limits. And another little trick, I don't know if it makes life any easier or not. I used to always do it. Well, I still do it. I just kind of write my integrals all together and then put my limits of integration way out to the side. So again, I don't know, maybe technically I should put this in brackets or something to indicate that I have to plug the limits into the entire integral. Okay, here we go. I'm going to plug in the upper limit now. If I plug in 2, I'll get negative ln of 2 times 1/2 minus 1 over 2. There's the upper limit. And then I'll subtract away the lower limit. I'll get negative ln of 1 times 1 over 1. And then I'll subtract away 1 over 1 from that. Make sure all my parentheses are in there. I think they are. And recall that ln of 1 equals 0. So this whole term is going to cancel out anyway. And, you know, negative ln of 2, it's not, without a calculator, you can't really do much simplification to ln of 2. So I would leave this term alone. Certainly, if I had to clean it up, I would distribute, get a positive 1 on the right-hand side, add that to the negative 1/2. But that's pretty much the idea on these. So you do them just like normal. Use your regular integration by parts stuff on them. And just remember that you just have to plug in your limits of integration as you go along.
Now in the end, let us summarize what we have learned in this lecture. A function f is an antiderivative of f if f dash equals to f. Every antiderivative of f is equal to f plus c for some appropriately chosen constant c. We write integration fx dx equals to f x plus c. Substitution method works provided the change of variable results in elimination of the original variable and leads to a simpler, more elementary integral. The integration by parts formula for functions u, x, vx is integration u dv, which is equals to uv minus integration v du. Integrals involving 1 plus minus x2 is simplified by making a trigonometric substitutions. Integrals with products or powers of trigonometric functions are simplified by application of trigonometric identities or simple substitution.